Hello and welcome back. Today we're going to continue looking at vectors. So remember with vectors, we have written vectors in component form and as linear combinations. And what we can do is whenever we have a vector in either form, we can actually determine the angle, which we call the direction angle. And that's really easy with the trig that we already know. So if we were to draw a triangle here, you can see right away that that angle will just be the tangent. So we just said the tangent of theta equals y over x. And in this case, we have the a representing the change in x and the b as the change in y. All right, so let's practice finding the direction angle for each of these vectors. So for each of these, I'm going to sketch the angle first, and you'll probably see it right away after I sketch it. So this is going to -6 in the x direction, and then +6. So when we have that vector here, we want to find this directional angle. And you could probably tell right away without any math that this is going to be a 45, 45, 90, right? These two would be congruent. And so if that was 45, well, we know that angle will be 180 minus 45, right? Or we could just write 135. Now I'm just going to show you how to find it if we didn't have the special triangle, just so that we're able to figure it out. So if you don't know the angle, well, you can use tangent. So we're talking about tangent of theta will be the change in the y over the change in the x, or the b over a. So this is just 6 over -6. And then if you're going to find the tangent of -1, remember the tangent is negative in quadrants 2 and 3, or 2 and 4, excuse me. And so we know that we can find the inverse of tangent. And so this angle right here would be 45. And again, you would get 135. So either using trig, just noticing with the drawing, or using that tangent. All right, let's try another one. We're going to find this direction angle given the vector as a linear combination. Again, we have that a, and we're going to draw the sketch so we can see this. So we're going, our change in x is -7, and we're going down -4. And let me just use a different color. So you could definitely see, well, probably don't know that angle, right? We don't have a special triangle. So we can find this angle using tangent, right? So the change in the y, which is -4, over the change in the x. And I'm just going to write that as 4/7, just to simplify that. And we know that tangent is positive in the first and the third quadrant, right? So if we took the inverse of tangent, or the arctangent of 4/7, and that'll give us this reference angle, well, we could add that to 180 to give us the full rotation. So if this is in degrees, right? Usually we've been working in radians as well. So in degrees, I'm just gonna make sure we write that. We're finding these measures in degrees. So 180 plus the arctangent of 4/7, and that's about 29.74. So 29.74, and we'll add those together. So that'll be 209.74 degrees. Okay, so finding those direction angles are not too bad. Just remember that you can use tangent, which is the change of the y over the change in the x. Okay, now let's look at some of these velocity problems considering airplanes. So each of these are very similar, but we're looking at a vector showing the velocity of the airplane. So it's descending at a speed of 100 miles per hour at an angle of 45 degrees below the horizontal. So let's just draw a picture here. So the 45 degrees below the horizontal, this is 45. And you can see that this is going to be the vector here for the airplane. So if we know that it's descending here, we know that we're also given, this is vector v, the magnitude, or the speed, right? So that's 100. And then you know that that angle is 45. So if I was going to find that whole angle, remember this would be 225, right? We'd add that to 180. So this angle is 225. So if we're going to write the component form for this angle, we write it's going to be the velocity or the magnitude times the cosine of 225, and then 100 times the sine of 225. That would give us this vector in component form. So I could simplify this pretty easily. We know that the cosine of 225, that's just going to be negative root 2 over 2. And then we know the sine is also negative. And we can simplify that pretty fast. So that's negative 50 root 2, negative 50 root 2. And just to confirm, you can go back and you could square those and make sure that the velocity is 100, right? So if you square those and add those together, take the square root, you'll get back to 100. So if we have a plane here, it's traveling at a speed of 724 kilometers per hour. I'm going to write this plane here as vector v. So the magnitude of vector v is 724. And it's flying at a bearing of north 30 degrees east. So let me just draw a little sketch here, but it's going to be here 30 degrees, right? So we can figure out that angle, that direction angle is just 60. You can see that right here, right? The direction angle is always going to start with a positive x-axis and go counterclockwise. All right, and then it's going to fly with the wind here, and I'm going to use a different color. The wind velocity, I'm just going to use W for wind, the vector. And so the magnitude of the wind is 32. And it's flying from the west. So if I wanted to find the west, right? So it's going, let me just see if I can do a directional here. But you can see right here, it's going to be just going to the west, or from the west to the east. Okay, so in a different direction. All right, so if we're going to have both work on, so the wind is acting upon the plane. So if we look at this plane, I'm just going to draw a little picture here and put those vectors together. We know the plane is going in this direction. It's flying very fast, okay? So it's going to be just probably affected just a little bit by that wind. And so if we have that sum, those two vectors added together, this orange would show the actual path of the plane. So we want to find the true speed, right? The true magnitude of the plane and direction, right? With the wind acting upon it. So again, for this one, we're going to put each of these vectors into component form, and then we can add those two vectors together to make the resultant vector, or the resultant, I should say. So considering this, we know that for the plane, this will just be 724 cosine of 60, 724 sine of 60. So that's vector v. And then vector w is going to be 32 cosine 0, 32 sine 0. Put a 0, not theta there. All right, so we can simplify that pretty easily. So let's first simplify these 60. So we know that 724, well, cosine of 60 is just 1/2. And then sine of 60 is root 3 over 2. So I'm just going to simplify this. So this is 362, and this will be 362 root 3. And then considering the vector for the wind, we know cosine of 0 is just positive 1, right? So that's just going to be 32. And then the sine of 0 will be 0, so that'll just be 0. So again, we're going to add these vectors together. So we put them together. Let's try to stick with orange here. So v plus w In component form, it'd just be 362 plus 32. So what's that? 394. And then 362 root 3 just plus 0. All right, so that's the vector. That's good. Now we can actually use this vector to find the magnitude. So we just have to use the distance formula. So we just put that in the square root, so that's just going to be 394 squared plus 362 root 3 squared. Right, so that magnitude will round it a little bit, but it'll be 740.5 kilometers. And then if we were going to find the angle, well, we just have to use the tangent again. Remember, so we talked about that earlier. So the tangent of theta, well, the change in the y is 362 root 3 over 394. Now to find the measure of that angle, we'll take the arctangent. So that theta will equal 57.86. We'll round it to 86 for the hundredths degrees. Now remember, that is the reference angle. And so if we wanted to figure out the direction angle, let's just draw this here. And I'll use a different color to try to get the reference angle. So remember, the reference angle, this angle will be in the first quadrant, and the plane is going in the direction north. So we have to find that complement of 57.86 and subtract that from 90, and we get 32.14. And that's going to be east. Try this next problem. Pause the video and come back to check your answer. All right, let's look at each of these vectors. So vector V has magnitude of 550, and I should have said bearing instead of direction, because this is going at 240 degrees with an air navigation bearing. So just to draw that out, we draw that from starting with the north, going clockwise, and then we can find the direction angle, making sure we add 180 to the 30 reference angle. So that angle is 210. And then to find the wind, well, that just has a magnitude of 85. And looking at that direction angle, we know that's going south, 45 degrees east. So we just have to add 180 to get the direction angle 315. So we can find vectors V and vectors W by using the magnitude, multiplying the magnitude times cosine of the angle for the horizontal change, and the magnitude times the sine of the angle for the vertical. And then we can put them together to find V plus W. After we have the component form, we can find the magnitude, which is 534.35 miles per hour. And then we put them together. Tangent of theta is B over A, and we can find the reference angle is 38.84, and then the direction is south, 51.6 degrees west, right, because it's starting south. And then if we want to find the true bearing, well, we can add just 180, so we get 231.16 for the true bearing. Okay, let's try another one. Let's first look at the problem. Pause the video and come back to check your answer. Okay, let's check your answer. So considering plane V, vector V, it has a magnitude of 500, and you'll have to make sure that you draw and figure out the angle, given that it's an aerial navigation. So we know that that angle will be 120 degrees. So we can simplify that. 500 cosine 120, 500 sine of 120. In component form, that vector would be negative 250, and then 250 root 3. So that's going to be in the third quadrant. And then for vector W, representing the wind, we know that that's going to have a magnitude or speed of 70 miles per hour. And then again, you have to find the angle, but it's not too hard. We know that that angle will be 45 degrees, and that's in the first quadrant. So when we simplify that, we'll get 35 root 2 and 35 root 2. Now we're adding these vectors together to get the actual direction and speed of the plane. So I do get some crazy numbers, but they're not too bad. So what I'd like to do is if at all, whenever possible, try to keep them in exact form until the very end if you have to round. Okay, so the vector v plus w is negative 250 plus 35 root 2, 250 root 3 plus 35 root 2. A little crazy, but not too bad, right? And then to find the magnitude, we have to use the distance formula, all right, or the Pythagorean theorem, whichever you want to think of. So we add those together and then take the square root. So we get 522.51 miles per hour for the speed. So originally it was going 500 miles per hour, and that wind picked it up to go a little bit faster. So looking at this, we can actually find the angle, right? So again, the angle is the sine over the cosine, that change in the y over the change in the x, and we get a negative 67.43. So just be really careful because tangent is negative in the second quadrant. So the bearing will be north 22.565 degrees west, or 337.35 degrees for the true bearing. Okay, let's switch gears a little bit, a little pun on physics. We're going to look at static equilibrium or balance of these two cables. I'll just label this as T1. And there's another tension on this other triangle. I'm going to use a different color, T2. Okay, so, and that's what's really holding that weight up. It's balanced against two forces, a horizontal force and a vertical force. So we're going to put the scenario into two vectors, okay, in component form. So we want to break it down into horizontal and vertical. So what I'm going to do is label this first triangle here. So this horizontal, I'm just going to put, this is my TX1. And then my vertical, I'll make this my TY1. Now looking at the second triangle, I'm going to label the same idea here. I'm going to make this my TX2. And I'll make this horizontal, that's the horizontal, and then this is the vertical, the TY2. All right, and so we could use some basic trig to find those sides. So if we wanted to find, I'll first start with this over here, the TY1. So if we know that this angle is 55, then we know the sine of 55 equals TY1 over T1. So if I wanted to isolate TY1 would equal T1 times sine of 55. I'm going to put those little blocks here. So that's going to be right here. So that's how I can represent that with some trig. And then for the TX1, I could do the same thing but use cosine. So cosine of 55 would equal the adjacent, which is TX1 over T1. And then so I know that TX1 equals T1 times the cosine of 55. I'm going to do that for the second triangle as well. So I'm going to represent this TY2 in terms of sine, but now we know this angle's 37. So sine of 37 equals TY2 over T2. So TY2 equals T2 times sine of 37. Component right here is the TX2, so cosine of 37 would equal TX2 over T2. So my TX2 would be equal to T2 times the cosine of 37. So there's actually two forces that are acting on this weight. So the first thing is that this is static, so it's equilibrium. It's not moving. So we know that the two x values have to equal each other. So this pull to the left, this pull to the right must cancel each other out because that weight is not moving side to side. So our TX1 must equal our TX2. So I'm just going to write that out. So we know that, use some substitution here. So we know T1 cosine 55 equals T2 cosine of 37. So that's going to be the horizontal. Now let's consider the vertical. So we know the 350-pound weight is pulling the cables down. So they must be counteracted or balanced by the upward forces because this weight is static again. It's not moving. So we're going to make sure that we write down that the vertical, the TY2 Ty1, that's right here, and the Ty2 should balance out the force of the weight. So we know that the Ty1, that was T1 sine of 55, and the Ty2 is T2 sine of 37. And for math, unlike physics, we're actually going to keep this in terms of pounds. So that'll be 350. We know that you change that to newtons in physics, but we're going to keep it in terms of pounds. Okay, so here we see a system of equations, and you can identify that we can substitute either variable. So I'm going to isolate T1 on this side. So T1 equals cosine of 37 divided by cosine of 55. And I'm going to substitute that in for the second equation. So we have T2 cosine of 37 over cosine of 55. And let me switch back to blue so you can see the original. So we have sine of 55 plus T2 sine of 37 equals 350. All right, so from here, what I'm going to do is do a little bit of algebra. So I'm going to factor out the T2. I want to keep this as exact as possible. So this is going to be cosine of 37 over cosine of 55 times sine of 55. You can write that in the numerator, plus sine of 37 equals 350. And so when I calculate that and simplify, this is about 1.74238. And when we divide 350 by that number, the tension is 200.874 pounds. And then we could just plug that number in for T2 and get the value or the force of T1. So let me just substitute that into this equation right here on the left. And we get T1 equals about, right? We're approximating, so I'm rounding, 279.693 pounds. Okay, so we have the tension from those two cables that are holding that 350-pound weight in balance. I hope this lesson was helpful, and I'll see you all in class.